This video is all about stoichiometry, which is a fancy word for something that's really not that hard and that you're going to be great at. So first up, what is stoichiometry? It's the process of using a balanced chemical equation to determine the relative amounts of reactants and products involved in a reaction. And why that might seem like a lot and might seem like something you don't know how to do, you already know how to balance chemical equations. And the rest of it, except for one step, is what we did in the last unit. So you're going to be great. Just kind of a silly stoichiometry example for you. We can think about s'mores, and we're going to be coming back to this reference later. But if we have 2 crackers plus 1 marshmallow plus 3 chocolate squares, that equals 1 s'more. Our equation is balanced. We have the same amount of things on every side. And we are looking at our relative amount of reactants to products. So what do chemical equations tell us? Chemical equations are essentially showing us chemical changes that involve the rearrangement of atom groupings as one or more substances change to new substances, like rearranging your room. We spent a lot of time on chemical equations last semester. So you can really think about it as how much reactants do you have versus how many products do you have. So before, when we were balancing chemical equations, we were just concerned with having the same amount of each element on each side. That was fine, you were great at it. And here's a balanced chemical reaction. So coefficients can be used to describe the reaction, literally telling us that for every 1 carbon and 1 oxygen and 4 hydrogens, 1 carbon, 4 hydrogens, and 1 oxygen is going to be produced. Can also tell us that carbon monoxide plus hydrogen gas is going to produce CH3OH. But they also, even though you didn't know it, tell us about moles and molecules, which is something we just learned about in our last unit. So for example, this carbon monoxide right here is actually telling us that we have 1 molecule of carbon monoxide, 6.02 times 10 to the 23rd molecules of carbon monoxide, and 1 mole of carbon monoxide molecules. And you guessed it, that means we have 2 molecules of H2 because of that coefficient in front, and 1 molecule of our product. We also have 2 times 6.02 times 10 to the 23rd H2 molecules, and 6.02 times 10 to the 23rd CH3OH molecules, and 2 moles of H2 molecules plus 1 mole of CH3OH molecules. So those coefficients can tell us how many moles of something we have. So just as a refresher on balancing chemical equations, it is the first step of all stoichiometry problems. I don't have time to completely reteach you how to do it, but the video is still out there if you need to rewatch it, but you guys were pretty great at balancing chemical equations. So just as a refresher, I want you to pause this video and balance this chemical reaction on your own. All right, let's see how you did. A correctly balanced chemical equation for this one would have no coefficient in front of there, which we know is a secret one, but we don't put the 1 there. 5O2 plus 3CO2 plus 4H2O. Literally telling us that for every 1 mole of C3H8 plus every 5 moles of O2, it's going to produce 3 moles of CO2 and 4 moles H2O. So this brings us to something called the mole ratio. So the mole ratio is the ratio of moles of one substance to the mole ratio of another substance in a balanced chemical equation. So for example, in the balanced chemical equation, 2Na plus Cl2 produces 2NaCl. So what is the mole ratio of sodium to chlorine gas? Well, it's every 2 moles of sodium makes 1 mole of chlorine gas. What is the mole ratio for sodium to sodium chloride? That's a 2 to 2 ratio. For every 2 moles of sodium, we get 2 moles of sodium chloride because of the coefficients in front. What is the mole ratio of chlorine to sodium chloride? That's a 1:2 ratio. 1 mole of chlorine produces 2 moles of sodium chloride. So why is the balanced chemical equation important? It's because we couldn't get this mole ratio without balancing the chemical equation. Those numbers are all coming from balancing the chemical equation. So we're going to use those as conversion factors. So this is the new part I was talking about. We're still using all of those great conversion factors we learned about before, but now we're adding one more to it, and that's the mole conversion factor, where you can say 2 moles of sodium equal 2 moles of sodium chloride. So let's talk about mole-to-mole relationships. So we can use a balanced chemical equation to predict the moles of a product that a given number of moles of a reactant will yield, or moles of a reactant needed to make a certain amount of a product. So moles are used instead of mass because each element and compound has a different mass. So we can't compare their masses directly, but we can compare their number of moles directly. Remember, a balanced chemical equation is needed to make a mole-to-mole comparison. If you don't balance the chemical reaction, you can't do this. The coefficients in a balanced equation will give us the mole-to-mole ratio, just like you saw on the previous slide. And we're going to use those mole ratios as conversion factors. So let's work an example together. Problem. In a synthesis reaction between nitrogen and hydrogen, how many moles of hydrogen is needed to make 4 moles of ammonia? So the first thing that we need to do is write out our chemical equation. So we write out N2, our nitrogen, plus H2, our hydrogen, produces ammonia, which is NH3. And when we balance it up, we need a 3 in front of the H2 and a 2 in front of the NH3. That part is review and something you should already be good with. Then we're going to determine the mole ratio needed. So for every 3 moles of hydrogen used, because we were asked how many moles of hydrogen is needed to make 4 moles of ammonia. So for every 3 moles of hydrogen used, it produces 2 moles of ammonia, NH3. We got that from our problem right up here. So for our third step, we're going to set up one of our little T-charts with conversion factors, and just like in our previous unit, we're going to start with what was given in our problem, and in this case, we were given 4.0 moles of ammonia. So we set up our problem, 4.0 moles of ammonia, and then on the bottom, we put our 2 moles of ammonia because we want moles of ammonia to cancel out. We put our 3 moles of H2O on the top because that's what we're trying to get to, how many moles of hydrogen. And when we do the math on that, we get 6 moles of hydrogen. Pretty straightforward, right? All right, then I want you to pause this video and try this one on your own, using the steps we learned on the previous example. Come back when you're done. Make sure to show all of your work. All right. So our first step, we need the balanced chemical equation. Same one as before. We need our mole ratio. Still, for every 3 moles of hydrogen used, but this time we're going to use 1 mole of N2 because we were asked how many moles of nitrogen are needed. So we were connecting hydrogen and nitrogen. Then we're going to set up our T-chart, starting with what was given, the 6.0. And you should have had 6.0 moles of hydrogen, 3 moles of hydrogen on the bottom, 1 mole of nitrogen on the top to get 2 moles of nitrogen needed. See? You're great at this. Let's try another example. For a synthesis reaction between hydrogen and oxygen to make water, answer the following. How many moles of water are produced when 5.00 moles of oxygen are used. If 3.00 moles of H2O are produced, how many moles of oxygen are needed? And how many moles of hydrogen gas are needed to produce 4 moles of water? So I want you to pause this video and try these 3 on your own. In this next slide, I'm only going to be telling you the answer, and I'm not going to be showing my work this time. Remember, if you don't have work shown on your notes, I'm not taking them, so make sure you pause this video and try it on your own. All right, let's see how you did. For A, for how many moles of water are produced from 5 moles of oxygen, you should have gotten 10 moles H2O. For B, you should have gotten 1.50 moles of O2. And for C, you should have gotten 4 moles of H2. If you didn't, rewatch the earlier slides in this video and then try it again. You can always come with questions tomorrow. So we already talked about in our previous unit as the mole being this kind of go-between thing, that it connects mass, number of particles, and volume. Though we don't have conversion factors that connect mass to volume or mass to particles or particles to volume, but we can get to all of them by using the mole. And that's what we're going to do here. So in our previous examples, we were going from moles of one type to moles of another type. But you have all the skills you need now to actually convert to mass of one type to mass of another type, which is the much more practical version. You don't put something on a scale and it tells you that it's this many moles. It's going to tell you how many grams it is. So we need to be able to work in grams. So moles represent a number of molecules, and we can't count those molecules directly, just like I was talking about. So we need to be using weight, or more accurately, mass. So when you are given a mass of substance A and wanting a mass of substance B, it's pretty easy. First, we're still writing out a balanced chemical equation, just like you just learned how to. Then you're going to convert from mass A to moles of A, which you already know how to do and we learned to do in our previous unit. You're going to use the molar mass of substance A, just like we did before. And then you're going to convert from moles of A to moles of B, which we learned how to do just in those previous slides, using that mole to mole ratio. And then you convert from moles of B to the theoretical mass of B. I'm calling it the theoretical mass, which I know doesn't mean a lot to you now, but it's going to become important later. What we are saying is that if everything goes correctly, this will be the mass. And we're going to do that using the molar mass of substance B, which is no different than what we did in our previous unit. So the only thing that is different from going from mass to mass than what we did in our previous unit is this little mole ratio right there in the middle, which as you can see is a super easy number to get. You've got this. For my people who are more diagram oriented, here's what I just said in diagram form, where we can have the mass of A, we do a mole to mole ratio, and it gets us our theoretical mass of B. So let's do an example problem together so you can see what I'm talking about. So for our problem, oxygen gas has been produced by decomposing potassium chlorate. Potassium chloride is also produced. If 138.6 grams of KClO3, that's potassium chlorate, is heated and decomposed completely, what theoretical mass of oxygen gas is produced? All right, so how are we going to solve this? We're going to always start with a balanced chemical equation. We are given the number of grams of potassium chlorate, that's right there for us. So we must convert to moles of potassium chlorate, and because That's because our balanced chemical equation deals in moles instead of grams. Then we're going to use the coefficients in our balanced chemical equation to determine the mole ratio. And then our step 4 will be to use the molar mass of oxygen gas to calculate the grams of oxygen gas produced. So let's take a look at those steps in action. So up first, we're writing a balanced chemical equation. 2KClO3 produces 2KCl potassium chloride plus 3O2 oxygen gas. We're going to want to find the molar mass of potassium chlorate and oxygen gas. You should know how to do that already. If you don't know where these numbers come from, you really need to come talk to me. We need to find our mole ratio, and in this case, our mole ratio is that for every 2 moles of potassium chlorate, 2 from right there, produces 3 moles of O2 right there. And then we are ready to set up our problem, and we're going to set it up like this. We put our number given from the problem, 138.6 grams of potassium chlorate first. Then we use our first conversion factor, where we need grams on the bottom for them to cancel out. We put the molar mass of potassium chlorate, 122.55, and we know that equals 1 mole. So now we are in moles of potassium chlorate, which means it's time for our mole ratio. We put the 2 moles of potassium chlorate down there because we need them to cancel out, and we put our 3 moles of O2 up at the top. We are now in moles of O2, but that's not what the problem asks us. It asks us about grams of O2. So we have one more step to go, where we know for every 1 mole of oxygen, we have 32.00 grams of oxygen gas. Then we multiply the top, divide by the bottom, and we get 54.29 grams of O2 being produced. I know these are a little bit tricky, but I want you to try this one on your own. But let's think about some things first. First up, our problem is a chemical reaction between diboron hexahydride and oxygen gas will produce oxoboronic acid, HbO2, and water. 2 questions for you. What mass of oxygen will be needed to burn 31.6 grams of diboron hexahydride? And B, theoretically, how many grams of water are produced from 19.2 grams of B2H6? So some questions for you to consider before you dive into this. First off, what is always that first step? That's right, balance that chemical equation. What information is given to you? What do we want to determine? Keep in mind there are 2 questions, so we're trying to determine 2 different things. What information do we need to know? What is the mole ratio? And now I want you to pause this video and try to solve these 2 problems on your own. Come back when you're done. All right. So your balanced chemical equation should have been B2H6 plus 3O2 produces 2HbO2 plus 2H2O. Which means for our mole ratio, we have 1 mole of diboron hexahydride reacts with 3 moles of oxygen to produce 2 moles of water. We're going to find the molar mass of each of those things. Once again, something we've done before. And then we're going to actually solve our 2 problems. So for part A, you should have written out what you see here. So this is our molar mass of diboron hexahydride. There's our mole ratio, there's our mass of oxygen, and we got our number in grams just like we wanted. For B, we have our starting number, same molar mass for diboron hexahydride, different mole ratio because we were comparing different things, different molar mass because this time we're talking about water, and we got this answer. Once again, for those of you who think more in diagrams than in words, this is exactly what we did today, where we can connect all of these things together where we have this side is given in the problem, and when you're asked for this side, you can follow this chart through to the end. Come to class tomorrow, ready to practice more stoichiometry.